Hi, this is week 14 of AP Physics, and in this week we'll be covering the following topics. We'll start with gravitational potential energy, then we'll move into gravity and conservation of mechanical energy. For our lesson objectives, students will learn how the elevation of an object increases its gravitational potential energy, and we'll also learn how mechanical energy is conserved in a system. So let's begin with gravitational potential energy. So potential energy is the energy possessed by a body by virtue of its position relative to others. For example, we have our high diver here who's well above the surface of the water. So since she's above the surface of the water, she's got gravitational potential energy. Stress within itself. So for example, the pole here for a pole vaulter is very much stressed since it is flexed. And it has potential energy to pull the pole vaulter up. And electric charge, so this battery right here would be a great example of chemical potential energy. So once plugged in, that battery could do work. Now, gravitational potential energy is the one we're going to focus on for this lesson. That is the energy possessed by an object because of its position. The further that object is above the ground, the more potential energy it possesses. So for our formula, a lot of the books use for potential energy the symbol PEG, so potential energy due to gravity for the G. But for AP Classroom, we're going to go ahead and use the symbol UG. So here, potential energy is equal to M times G times Y. Alright, M is mass measured in kilograms. The G is gravity. Gravity is 9.8 meters per second squared, but for us, we'll just stick to using 10 meters per second squared. And Y is its position relative to the starting point. How far above is the object above that starting point? So now let's talk a little bit about that. It says the change in gravitational potential energy is calculated using this formula. So that's your change. So how far up have you gone? And it depends on its reference points. The reference point is where you're starting from. So for example, this physics book being dropped on the table, and how much potential energy does it have relative to the table? So the reference point is the table. What about the same book dropped all the way to the floor? Again, now the reference point becomes the floor, so now you would say, well, that book, letter B, has more potential energy than letter A. And what if we toss the book out the window, and now the reference point would be the floor, so letter C would have much more potential energy because the reference point is much lower than in the previous A and B. Okay, so the reference point, that'll be the 0 point on the y-axis. Now, we're going to go ahead and move on to example number 4. In this one, they tell you, say you have a skier. Her weight is 60 kilograms, and this skier is at the top of a slope at point A. And this point A is 10 meters from point B, measuring that straight up. Not the length of the path, but how high is it? So point A is 10 meters above point B vertically. So next they ask you guys in part A, setting the zero level for the gravitational potential energy at point B, so I'll be at the very bottom, find the gravitational potential energy of the system when the skier is at point A and when the skier is at point B. Alright, so we're going to go ahead and solve that problem. And again, a drawing is always best. So here we have our skier, and our skier is going to go ahead and go down the slope. And at the very, very top, that's point A, it's 10 meters. That's point A. And at the very bottom, that is 0 meters. So that is point B. Alright, so one more time, the question was, find the gravitational potential energy at point A. That's the first part. So at point A, we're going to say, well, gravitational potential energy is equal to the mass of the skier, which was given to us. Her mass is 60 kilograms. So that's going to be our mass, 60 kilograms. Gravity is going to be 10.0 meters per second squared. And the height, so it's going to be 60 kilograms multiplied times 10 meters per second squared multiplied times the height. She is 10 meters above the ground. So you go ahead and you multiply all of these together and you get ahead and get 6,000 joules worth of potential energy at point A. Next they ask us also find at point B. At point B, again we use the same formula for gravitational potential energy. The mass remains the same, gravity due to Earth remains the same, but it's only the height that is changing. Now she is at the reference point, and that is 0. So it's going to be 60 kilograms, 10 meters per second for gravity, and 0 meters of height. So therefore her potential energy is 0 joules. She's got no potential energy since she is at the bottom of the hill. Alright, so next they say finally find the change in potential energy of the sphere Earth system as the sphere goes from point A to point B. So what is our change in potential energy? So our change in potential energy is going to be, let's see, mass times gravity times height. In this case it's going to be final minus mass times gravity times height initial. Final minus initial. We can go ahead and change this formula a little bit since we have the same mass and same gravity. We're going to factor them out. So we're going to mass times gravity times final minus initial. Alright, and symbol for that will be just delta H. So mass times gravity times delta H, change in height. So now we can go ahead and plug in the values for it. Her mass remains the same, 60 kilograms. The height remains gravitational pull, 10 meters per second. And the height, final minus initial, so it's going to be 0, that's the final, minus the initial. So 0 minus 10, that will give us a negative 10 meters. So our answer, once we plug all of that in, will be a negative 6,000 joules. So that'll be her change in gravitational potential energy for this problem. In part B of example 4, they ask us the following. Repeat this problem again, but this time the 0 reference point is at A. So therefore B is 10 meters below the 0, so we're going to label it as negative 10. So they want us to find the gravitational potential energy at A, at B, and the change in potential energy as well. Okay, so we're going to go ahead and begin with our formula. Formula for gravitational potential energy, it is UG equals mass times gravity times the height. Here the height's going to be 0, so let's see, we're going to go ahead and put the 60 kilogram mass. Acceleration due to gravity, 10, and 0 meters of height, so that gives us 0 joules. For the answer for point B, it's going to be 10 meters below 0, so it's negative 10. So we're going to go ahead and have potential energy due to gravity's mass times gravity times height, so it's going to be the same mass. Acceleration due to gravity, and our height is negative 10 meters. So you go ahead and multiply, that gives you negative 6,000 joules. What's the change in potential energy? Change in potential energy will be final minus initial. So you can say change in potential energy due to gravity, it is final, which is 6,000 joule, minus initial, 0 joules. So you get an answer of 6,000 joules change in potential energy from point A to point B. In part C of example 4, they ask us to repeat the following questions, which is find the gravitational potential energy at point A, point B, but this time they're going to say the reference point is just 2 meters above point B. So right here, about 2 meters above point B, that is our reference point, so that is our 0. So therefore point B is 2 meters below the reference point, and point A is 8 meters above the reference point, and so they're going to want us to find the gravitational potential energy here, and the difference in gravitational potential energy. So let's go ahead and begin at point A. Now our height is 8, so let's see, it's going to be gravitational potential energy equals mass times gravity times height. So the mass of the sphere remains constant, that is 60 kilograms. Acceleration due to gravity, 10 meters per second square, and this time our height is 8 meters above the ground, above the reference point I should say. So it's going to be 60 times 10 times 8, that gives us 4,080 joules. Next, for point B, it's mass times gravity times height to get the gravitational potential energy. Mass of the sphere, 60 kilograms, 10 meters per second squared, acceleration due to gravity, and our height is 2 meters below our reference point, so that's going to be a negative 2. So that's going to go ahead and give us the following, 60 times 10 times 2 negative, negative 1,200 joules. All right, and one more time we're asked to go ahead and figure out, so what is the change in potential energy from point A to point B? So our change in gravitational potential energy is going to be final minus initial. So our final was negative 1200 joules minus initial, which is 4800 joules, and again we get negative 6000 joules. So the change in potential energy is always negative 6000 regardless of where we put the reference point. And that takes us to the end of example number 4. Up next is problem number 11. In this problem they ask you guys the following question. If the angle of slope is increased, does that change the gravitational potential energy between the two heights? So this is what they're saying. Maybe we're going to increase the angle even more, so it's going to be even steeper. But you're still going from point A to point B. How does that affect the answer? And the answer to that question is letter C. It remains the same. The angle of the slope is irrelevant as long as you travel a height of 10 meters. Then the gravitational potential energy will remain the same. Let's go ahead and move along to problem number 12. And problem number 12 says, if the zero level for the gravitational potential energy is selected at the midway point, which is 5 meters above point B, find the initial potential energy and the final potential energy and the change in potential energy as the sphere goes from point A to point B. So let's go ahead and do that one. So again, our reference point one more time. The 0 point is going to be halfway through. So therefore, A will be 5 meters above and B will be 5 meters below our reference point. So they want the gravitational potential energy at point A, point B, and the change in gravitational potential energy. So that's our height right here relative to our reference point. So for point A, it's going to go ahead and be mass times gravity times height. So the mass is still 60 kilograms for our skier. Gravitation, 10 meters per second squared. Acceleration due to gravity, and the height is going to be 5 meters. For this one, you go ahead and plug it into a calculator, it'll give you 3,000 joules. For point B, it's going to go ahead and be the following. Same mass times gravity times height, 60 kilograms, 10 meters per second, acceleration due to gravity, 10 meters per second squared, and it is 5 meters below the reference point of 0. So it's going to give us negative 3,000 joules. So what is our change in potential energy? Change in gravitational potential energy is equal to final, negative 3,000 joules, minus initial, 3,000 joules. And again, it is 6,000, because as mentioned earlier, the reference point was not going to change the fact that point A and point B are 10 meters away from each other. So that's why you always end up with the same change in potential energy regardless of where the reference point is. That takes care of problem number 12. Next for us, we're going to go ahead and discuss gravity and conservation of mechanical energy. So here it states, when a physical quantity is conserved, the number value of the quantity remains the same through the physical process. Although the form of the quantity may change, its final value is the same in its initial value. Alright, so what they're trying to talk about right there is how energy is conserved. For example, if I were to hold this remote above my hand, so the reference point is my hand, and I hold it, does it have potential energy? Sure, it has potential energy due to gravity. Once I let it go and it starts falling, it's going to go ahead and lose that potential kinetic energy due to gravity because it has less and less height. But as it is falling, it's also gaining velocity, so now it's gaining kinetic energy. So whatever amount of potential energy is lost as it's moving down is also gained by speeding up, so therefore it develops kinetic energy. And that value stays the same. If I lose 5 joules of potential energy due to gravity, I'm going to go ahead and gain 5 joules worth of energy due to kinetic energy. So it's going to be the same, so they're saying we're conserving these energies. Alright, so there are two general kinds of forces, conservative and non-conservative forces. So conservative forces are those that we can easily conserve. For example, the height of this remote above my hand, let's say it's about half a meter, then we can go ahead and easily conserve it. When we bring it down, bring it back up again, it's going to gain the same amount of potential energy due to gravity. So that was a conservative energy. Now, non-conservative, these are forces that tend to dissipate. They go away. For example, to produce sound, you need a force. It's going to create a wave. So there's a sound that created by clapping my hands. There was a force there, and that sound dissipated around the room. Could I go ahead and collect the sound and store it for later? And this is no, I cannot collect the sound. It's gone. So that would be a non-conservative force. We did need force to create the sound. The sound wave went out, but we cannot store it. So therefore referred to as non-conservative. If we add up all the non-conservative forces with the conservative forces, then we get our mechanical energy. So the product of the sum of kinetic energy and gravitational potential energy is known as mechanical energy. So E equals K, which is kinetic energy, plus gravitational potential energy. So in this picture right here, this dog is fetching that ball right there, and that's a great example of an object that has both potential energy due to gravity, since the dog's above the water, so he's got potential energy due to gravity, but also he's got kinetic energy because he does have a lot of speed, and so both of them put together, that will give us our mechanical energy. So the law of conservation of mechanical energy in isolated systems states that the initial and final values of mechanical energy are conserved. So initial mechanical energy is the same thing as final mechanical energy. And of course, change would be final minus initial. So since they're the same, in a closed isolated system, that value would be 0. So we can go ahead and expand on this formula a little bit. So where we have our initial mechanical energy is kinetic energy initial plus potential energy due to gravity initial. And on the other side, we have our final mechanical energy, which is final kinetic energy plus final gravitational potential energy. Now, the values for them, for K, for kinetic energy, is 1/2 mass times velocity squared. So now you see the formula now written out. And for gravity is mass times gravity times height. So there you see it as well. Same for the right-hand side. You will notice that across this whole equation, what do you notice that is the same? The mass. The mass is the same throughout. So what we can do in this type of problems to simplify it is we can go ahead and cross it out. So we end up with this formula as well. So which is 1/2 the initial velocity squared plus gravity times initial height is equal to 1/2 velocity final squared plus gravity times final height. And those sides will be equal to each other. So we're going to go ahead and use that formula quite a bit in the next few problems. Let's go ahead and take a look at problem number 13. In this problem, they tell you as the following. It says, you have 3 identical balls are thrown from the top of a building, all with the same initial speed, as seen in the picture right here. They ask you, rank the speed of the balls as they reach the ground. Alright, so one is thrown down, that's be number 3, one's thrown slightly up, and the other one horizontal. So which one will have more velocity as it hits the ground? The answer is all 3 of them will have the same velocity as they hit the ground. All 3 of them will. Why is that? Well, if I throw the object, let's say I throw it straight down with a velocity of 2 meters per second. So I throw it down at 2 meters per second. Alright, so it's going to pick up speed because gravity is accelerating the object, and it's going to hit the ground, let's say some velocity. But keep that in mind, my reference point is the hand, and I threw it at 2 meters per second. Now on the other hand, what if I throw it up at 2 meters per second? Alright, once I throw it up, it's going to go up and then stop at some point, come right back down. But when it reaches the point where I left it, which is again my reference point, how fast is it going to be going when it reaches my reference point? Same thing, at 2 meters per second down, which is the same as the previous one I tossed. So therefore it's going to have the same velocity. So all 3 objects will hit the ground with the same velocity. Now, which one will take longer to hit the ground? Well, number 2 will take longer, so you have to go up and then come back down. Number 3 will be the fastest, and number 1 will be somewhere in between. Nevertheless, all 3 objects will hit the ground with the same velocity. Alright, let's go ahead and take a look at problem number 14. In problem number 14, you have Bob of mass m. Here he is on a tree. He drops from a tree limb at the same time as Esther, also of mass m, begins her descent down a frictionless slide. So this slide has no friction. Okay, if both start at the same height above the ground, which of the following is true about their kinetic energy as they reach the ground? Alright, so they both have the same potential energy because they have the same height. but now as they're both moving down, they're losing that kinetic energy and it's converting into kinetic energy. So they're losing their potential energy into kinetic energy. So now, who's going to have more kinetic energy? So the answer A, Bob's kinetic energy will be greater than Esther's. Letter B, Esther's will have more kinetic energy. Or C, both will have the same kinetic energy. The answer for this problem is C. They have the same kinetic energy because they both have the same potential energy, so therefore they'll have the same kinetic energy. Now, that's true for this problem where we have a frictionless slide. In real life, there is friction in the slide and Esther would lose some of her energy due to friction. But for this problem, because they said frictionless, the answer is C. They both have the same kinetic energy. Alright, that takes care of problem number 14. Up next for us is example 5. And in this example, they ask you as the following. A diver of mass M drops from a board 10 meters above the water surface. Use the conservation of mechanical energy to find his speed at 5 meters above the water surface, and in part B at right before he hits the water. So 10 meters of height, mechanical energy, that's going to be our formula we're going to go ahead and use. So mechanical energy initial is equal to mechanical energy final. So what are we going to do here? Well, what is mechanical energy? It is our potential energy plus our potential energy due to gravity. So kinetic energy is K initial plus potential energy due to gravity initial, and that's equal to our kinetic energy final plus our potential energy due to gravity final. What's the formula for kinetic energy? Kinetic energy is 1/2 mass times velocity squared. So we're going to substitute that here. So it's going to be 1/2 mass times velocity squared initial plus formula for potential energy due to gravity. It is mass times gravity times height initial. On the other side, it's going to be the same, but we're going to go ahead and replace with final. Mass times gravity times height final. Alright, so that is our formula. Now what are we looking for? We want the velocity of the diver. So we're really looking for VF. That's what we want. So we're going to go ahead and isolate everything, get rid of as much as we can, and isolate the VF. Alright, first let's simplify this. Notice that the mass is the same throughout, so we can go ahead and factor it out and divide it. So it's gone, divide everything by m, so we end up with this 1/2 velocity initial squared plus gravity times height initial. It's equal to 1/2 velocity final, which is what we're really looking for, plus gravity times height. Alright, what else can we get rid of? Well, I want to isolate the VF, velocity final, so I'm going to move this gravity times height final over to this side. So notice that's a positive, so I'm going to do it by subtraction. So now I have this 1/2 velocity initial squared plus gravity times height initial minus gravity times height final. It's equal to 1/2 velocity squared. Again, I want to isolate this right here. But before we do that, let's go ahead and work over on this side. What is velocity initial? Well, the diver was just the instant he had just left the board, his velocity is 0. So that's a 0. So I'm going to go ahead and get rid of it because 0 squared times 1/2, who cares, gone. So we're left with this. I want to factor out the g, so I'm going to move it out. So it's going to be g height initial minus height final is equal to 1/2 velocity squared. So now that's our formula. I want to get rid of the half because I want to isolate the VF. So I'm going to multiply both sides by 2. So now we're left with this formula. And finally, I just want V final, not V final squared. So I'm going to square root both sides so I can get rid of the squared. So we're left with this. This is our formula. Square root of 2g multiplied times height initial minus height final. And that is our formula. So for part A, they want to go from the initial height to a height of 5 meters. So let's go ahead and plug it into the formula. And so for part A, it's going to be velocity final is equal to 2 multiplied times gravity, 10 meters per second squared. And initial height, the diver was at the top of the board, so he was at 10 meters. And for part A, they want it at 5 meters above the ground. And we go ahead and square root all of this. So it's going to be, that is 5 times 6, 10. So square root of 100, that's going to give us 10 meters per second. Alright, so that is the velocity at part A when he is going at 5 meters. Now, how much velocity does he have as he goes another 5 meters? Well, let's go ahead and plug it into the formula and figure that one out. So velocity will be 2 multiplied times gravity, and that's going to be 10 minus 0. So from the top of the board all the way down to he's at the 0 reference point, square root of that, so that is 10. 10 times 10 is 100, times 2, 200, and then you square root it. Square root of 200 will give us roughly 14.1 meters per second. So that is our answer for part A when he is at 5 meters, and at part B when he's just above the water. Alright, that takes care of problem number 5. Up next for us, we're going to go ahead and take a look at problem number 15. It says, qualitatively, how will the answer change if the diver takes a running dive off the end of the board? So now he's running as he jumps. Now the velocity on the y-axis, the answer for those will remain the same as in the previous problem, so those will not change. But what the diver did is now he added an velocity on the x-axis. So he added an x-axis component to his velocity. So this on the y-axis will remain the same as the previous example, but now this one is new. So what will be his total velocity? Will be this one, total velocity. Alright, so that will be actually longer since that's the hypotenuse. That will be longer. So now he'll have more velocity before hitting the water because of the added x component to his velocity. In problem 16, they ask you guys the following question. Suppose the diver vaults off the springboard, leaving with an initial speed of 3.5 meters per second upwards. Use the energy conservation formula, here we go, to find the speed when he strikes the water. So he's still 10 meters off the ground, but now he's using the springboard. So it's 10 meters high, but the springboard, he's jumping off of the springboard with an upward speed of 3.5 meters per second. So they want us to go ahead and use the same formula to go ahead and figure out what is his velocity. Now, change from this problem to the previous one is that now he does have an upward velocity, an initial velocity of 3.5 meters per second upwards. So let's go ahead and get the formula again. Mechanical energy initial is kinetic energy plus gravitational potential energy initial plus kinetic energy final plus gravitational potential energy final. What is the formula for kinetic energy? 1/2 times mass times velocity squared. It's going to be 1/2 mass velocity squared initial plus a mass times gravity times height initial. It's equal to 1/2 mass times velocity final squared, which is what we're looking for, plus mass times gravity times height final. Alright, so that's going to be our formula. What can we get rid of? We can go ahead and get rid of the mass. Notice that the mass is irrelevant because it cancels out throughout. So we're going to go ahead and do that, get rid of the mass. So we're going to be left with this. 1/2 velocity initial squared plus gravity times height initial. 1/2 mass times, no, mass is gone, velocity final square plus gravity times height final. Alright, so what else can we do to this? Well, we can simplify a little bit. I'm going to go ahead and multiply the whole thing by 2 just to get rid of the halves. Alright, so it's going to be velocity initial square plus gravity times height initial times 2. It's going to equal velocity final square plus 2 times gravity times height final. I want to go ahead and get this, move it over to this side, combine some like terms. So I'm going to go ahead and notice that that is a positive, so I'm going to do it by subtraction. So we're going to go ahead and be left with this. Velocity initial squared plus 2 times gravity height initial minus 2 times gravity times height final, and that is our velocity final squared. We can go ahead and factor out the 2g just to simplify this a little bit. So it's going to be velocity initial square plus 2g height initial minus height final, and that is our velocity final squared. And we're going to go ahead and square root this so we can go ahead and just get the velocity final. So we're going to go ahead and end up with this velocity initial squared plus 2g height final minus height initial, square root, and that will be our formula to solve for this problem. Velocity initial is going to be 3.5 positive because he jumped up. Had he somehow managed to use the springboard to give himself velocity 3.5 going down, we'll put a negative 3.5. Alright, so we're going to go ahead and substitute the values in. Velocity initial is 3.5 meters per second. We're going to square that, plus 2 times acceleration due to gravity, multiply by initial height minus final height. So he was initially at 10 meters above the water, now he's at 0 meters right before he hits the water. So it's going to be 10 meters minus 0 meters, and this whole thing is going to be square rooted. So let's get the calculator and go ahead and solve. So it's going to be 3.5 squared. That gives us 12.25 plus, it's going to be 10 times 10, that's 100 times 2 is 200. All this is square rooted. So that's going to be 200 plus 12.25, and we're going to go ahead and square root it, and that's going to give us a final velocity of 14.6 meters per second. So that is the velocity of our diver after he went off of the springboard as opposed to the platform when he was at 14.1 meters per second. That takes care of problem number 16. Up next is example 6, and in this problem they ask you as the following. Water slides are nearly frictionless. So one such slide says the Der Sturka, named for the German dive bombers in World War II, is 72 feet high, which is about 21.9 meters, and it's found at Six Flags in Dallas. So in part A they ask you to determine the speed of a 60-kilogram woman at the bottom of the slide. So that's going to be our first question for part A, and we're going to go ahead and use the same formula we derived in the previous problem. So here it is, velocity final is 2 times gravity times the change in height. So for velocity final it's going to be 2 multiplied times gravity, 10 meters per second, and the initial height is 21.9 meters, and at the bottom of the slide, what is the final height? She's at the bottom, so that is 0. Okay, so that will be our setup. Go ahead and get your calculator. You go ahead and subtract first, parentheses first. So it's going to be that minus that is the same value, 21.9 times 10 times 2. Then we square root it. And her velocity is 20.9 meters per second at the bottom. Alright, so that takes care of part A. In part B, they ask you the following question. If the woman is clocked at 18 meters per second, so instead of going at 20, she's clocked at 18, at the bottom of the slide, find the work done on the woman by friction. Alright, so for that one, we're going to go ahead and use work, non-conservative. Yeah, you cannot conserve friction. You can't store it. You can't put it in a jar. So that's going to be the formula, which is equal to if you add up the change in kinetic energy plus the change in potential energy. So this is going to be our formula. Alright, so how do you get change in kinetic energy? It's kinetic energy final minus kinetic energy initial. So I'm going to go ahead and substitute that in. So kinetic energy final minus kinetic energy initial plus change in potential energy is going to be potential energy due to gravity final minus potential energy due to gravity initial. Alright, so that will go ahead and give us our work, non-conservative. So the work, what's working on this is friction doing work over the distance of the slide. Alright, so now they ask you guys the following. Okay, so what's going to be the value for that one? We can make this formula a little bit simpler by getting rid of a couple of values. Number one, kinetic energy initial. As soon as she begins her run, how fast is she going the instant she decides, okay, let's go? The answer is 0. Velocity is 0. So therefore we can say, well, kinetic energy initial is not there. At the bottom, once she reaches the ground, how far off the ground is she once she reaches the ground? Well, her height is 0. So her final height is 0, so her final potential energy is 0 as well. So that's gone as well. So now we can simplify this formula. Notice the negative there. So we're going to simplify the formula to be this. Kinetic energy final minus gravitational potential energy initial. Alright, and once we find the difference, that will give us the work, which will be, that's the work done by friction. Next, let's see, formula for kinetic energy final. Just go ahead and substitute that in. That is 1/2 mass times velocity squared. Mass times velocity final squared minus, in this case, it's going to be potential energy due to gravity, mass times gravity times height initial. Alright, so now we just got to substitute the values in to go ahead and get our answer for the work done by friction. So let's go ahead and do that. It's going to be 1/2 the mass of the woman was 60 kilograms. Her velocity final was 18 meters per second minus her mass was 60 kilograms times gravity times the initial height. The height of this water slide is 21.9 meters. Alright, so there's all of our values. I'm going to go ahead and plug them into our calculators and go ahead and solve. So it's going to be 18 squared times 60 times 0.5. That's going to go ahead and give me a value of 9,720 joules minus the other side 21.9 times 10 times 60. It's going to go ahead and give me 13,140 joules. And now subtract both of these to get my final answer. And I get a value of negative 3,420 joules. Alright, that's how much work is done by friction. Why is the answer negative? Well, friction is working against our woman who's sliding down the slide. So it's working against her. So that's why it has a negative value. So that's how much work was done by friction. Alright, that takes care of part A and B of example number 6. Up next for us is problem number 17. In this problem they ask you guys, if the slide were not frictionless, would the shape of the slide affect the final answer, and explain why. If the slide were not frictionless, yes, the shape of the slide would affect it. If you have a longer slide, that would go ahead and give you the ability for the friction to do more work. Since we're increasing the distance, we're also increasing the amount of work that friction is doing on them. So therefore the shorter slide will give you more velocity. The longer slide, there'll be more friction because there's more distance, so the friction will be able to do more work, and therefore you will go slower. So yes, the shape does affect it if there is friction. What if it was frictionless? Then the shape would be irrelevant. In problem 18, they ask you, suppose a slide similar to the Der Stucke is 35 meters high, but straight slope inclined at 45 degrees with respect to the horizontal. Part A, find the speed of a 60 kilogram woman at the bottom of the slide, assuming no friction. Since there's no friction, the angle here does not play a role. So therefore, it's really irrelevant to this problem. All we really need is the height to figure out the velocity of the woman at the bottom of the slide. So we're going to go ahead and say the following. Initial height is 35 meters. Final height at the end, which it gets to the bottom, we're going to say 0 meters. And the angle, which is irrelevant to this problem, is 45 degrees. And the mass of the woman, who's also relevant to this problem, is 60 kilograms. Alright, so the formula for her velocity in a frictionless slide, where there's no friction working on it, is this 2 times gravity times height final minus, height initial minus height final. And you get the square root of that. That's an equation we derived in an earlier problem. Alright, so you're going to go ahead and substitute your values in. It's going to be 2 times gravity, which is 10 meters per second squared. Height initial minus final is just 35 meters. And then we're going to go ahead and get the square root of that. So it's going to go ahead and be 35 times 10 times 2 will give us 700. And square root of 700 gives us 26.45. So we'll just round it off to 26.5 meters per second, which will be her velocity on this frictionless slide. That takes care of problem number 18, part A. In part B of problem number 18, they say, if a woman has a speed of 20 meters per second at the bottom, find the change in mechanical energy due to friction. So our change in mechanical energy, we're going to get the change in kinetic energy, and we add it plus the change in gravitational potential energy and put those together. Alright, so let's go ahead and begin. Work non-conservative is equal to changing kinetic energy, which is kinetic energy final minus kinetic energy initial. We're going to go ahead and add that to gravitational potential energy final minus gravitational potential energy initial. Alright, now we can go ahead and simplify this a little bit. At the very beginning of the run, the woman, the instant she begins, she's got no speed. So therefore, kinetic energy initial is at 0. So we can go ahead and get rid of this value. And at the bottom, once she reaches the floor, she's got no height. So therefore, gravitational potential final is not there. So that's gone. Alright, so kinetic energy final and gravitational potential initial are going to be the only ones who I'm going to go ahead and write down. So those are going to be kinetic energy final, it is 1/2 mass times velocity final square minus potential energy, which is mass times gravity times height initial. Alright, we can go ahead and plug in the values now. And let's see, we've got 1/2 the mass, which is 60 kilograms. Velocity 20 meters per second squared minus 60 kilograms. 10 meters per second squared, and 35 meters. Alright, so that would be your values plugged in. And let's go ahead and get our calculator and go ahead and solve for these. So it'll be 20 times 0.5 times 60. That'll give us 12,000. 12,000 newtons. And, oh, pardon me, 12,000 joules. And on the other side, it's going to be 35 times 10 times 60. It's going to give us 21,000 joules. So go ahead and subtract, and you get 9,000 joules of work. Negative 9,000 joules of work. And that will be the change in mechanical energy. Now for part C, they ask you as the magnitude of the force of friction. Alright, so we need to go ahead and figure that out. What's our force of friction? So it's going to be, our work is equal to the force times the displacement. So that's our work of friction right there. So we're going to go ahead and move this around a little bit so it looks like this. Friction is going to be then work, non-conservative, over the distance that she actually traveled. Alright, we have the value for the numerator, which is negative 9,000. Now we need the distance. She traveled 35 meters, well, on the y-axis, yes, but she also traveled the same on the x-axis. So we need this distance. That's how far she traveled. So we can go ahead and use, this is our opposite. So I'm going to go sine is opposite of hypotenuse. So it's going to be sine of 45. It's equal to opposite, which is 35, or hypotenuse, which is d. That's the distance we want. I rearrange this a little bit, so it is distance is equal to 35 over sine of 45 degrees. So that'll give us a distance. So let's see, sine of 45 is 0.707. So 35 divided by that answer, it gives us 49.5 meters. That is the distance she traveled from here to there. The height was 35, but it's a 45-degree angle, so she actually traveled that far. So it's going to be 9,000 joules divided by 49.5 meters. So that's going to go ahead and give us the friction, which is going to round it off slightly to 182 newtons of force that friction did on the woman from top to bottom of the slide to slow her down a little bit. That takes care of problem number 18. Up next for us, you'll come across problem number 19. And in this problem, they ask you as the following. It says a rubber ball with a mass of 0.2 kilograms is dropped vertically from a height of 1.5 meters above the floor. The ball bounces off the floor, and during the bounce, 0.6 joules of energy are dissipated. So it loses that much energy. So I'm going to put it as a negative because it's being lost. What is the maximum height of the ball after the bounce? So we're going to go ahead and use this formula where this is our energy that's going to be dissipated, and it's equal to kinetic energy, changing kinetic energy plus changing gravitational potential energy. So now we're going to go ahead and take a look at the kinetic energy. For the kinetic energy, it's got velocity final minus velocity initial. But when the ball is initially released, that instant is released, what's the initial velocity? The answer is 0. All right, so it goes to the floor, bounces, comes back up, and as it reaches its maximum height, what is the final velocity of the ball? Again, it's 0. So initial and final velocity in this problem are 0. For that reason, we're just going to ignore the kinetic energy since it ends up canceling out. So we're only going to use gravitational potential energy only. Alright, so what's changed? Well, that's final minus initial. So now our formula is going to be rewritten as this. Gravitational potential energy final minus gravitational potential energy initial. What are the values for them? Well, they're going to go ahead and be the following. That's going to be mass times gravity times height final minus mass times gravity times height initial. And the height final is actually what we're solving for. How high will the ball bounce after it disperses 0.6 joules worth of energy? Alright, so now we want to isolate that height final. So we're going to go ahead and move this over to this side. Since there's subtraction, I'm going to go ahead and add. So now our formula will look like this. Plus mg times hi equals mg hf. We're looking for hf, so I want to get rid of the m and the g, so I'm going to go ahead and divide both sides by it. And that's going to go ahead and give us our formula. mg gone. So there you go. That's height final is equal to this side of the formula. Now let's go ahead and plug in the values. So height final is equal to the work, which was 0.6, and that's how much dissipated, plus mass, which was 0.2 kilograms. And we're going to multiply it times gravity, which is 10 meters per second squared. And we're going to go ahead and multiply that times the initial height of 1.5 meters. And all of it will be divided by the mass times gravity. The mass, 0.2 kilograms times gravity, 10 meters per second squared. Alright, you plug that into your calculator and you're going to get the following values. So it's going to be negative 0.6 joules plus, let's see, 1.5 times 10 times 2. It's going to go ahead and give us 3 joules divided by 0.2 times 10, that's just 2 joules. So plug that into your calculator. So 3 minus 0.6 divided by 2, the answer is 1.2 meters of height. That is how far the ball will bounce up. It was dropped from 1.5, it'll come back up to 1.2 because some energy was dissipated. That takes care of problem number 19, whose answer is letter C, 1.2. Up next for us is problem number 20. Here we're asked, an apple is released from rest 500 meters above the ground. Due to the combined forces of air resistance and gravity, it has a speed of 40 meters per second when it reaches the ground. What percentage of the initial mechanical energy of the apple Earth system was dissipated due to the air resistance? And then they follow up by saying, take the potential energy of the apple Earth system to be 0 when the apple reaches the ground. And we get options as at A, B, C, D, 16, 40, 60, or 84% that was dissipated. Alright, so our initial height is 500 meters. So height initial 500 meters. The mass of the apple is not given to us, but we are given the final velocity. The final velocity is 40 meters per second. So Vf equals 40 meters per second. We can assume that Vi is 0 meters per second initial velocity, and final height, we're going to say 0 meters. Alright, so that's all the assumptions we have. Now let's go ahead and solve for how much energy was actually dissipated. So we're going to begin with what was our initial mechanical energy. Initial mechanical energy, which is kinetic energy initial, plus potential gravitational energy initial. Now, let's start with the kinetic energy. Initially, as soon as the instant the apple is released, the velocity of the apple is 0. So therefore, it's got no kinetic energy. So we can go ahead and cross that out. We'll just put the value for the gravitational potential energy. So that's going to go ahead and be mass times gravity times initial height. Alright, so now let's go ahead and plug in the values. We don't have the mass, but it's okay, we're not going to need it. So it's going to be mass times gravity, which is 10 meters per second squared, multiplied times the height, which is going to go ahead and be 500 meters. So our initial mechanical energy is going to go ahead and be 5,000 and times m. I'm going to leave out the units just to simplify this a bit, and the m is just the mass, so 5,000 m. Now what is our final mechanical energy? For final mechanical energy, it's going to be kinetic energy final plus gravitational potential energy final. Now one of these can go away, since at the end the apple reaches, the instant it reaches the ground, it is not off the ground anymore, so it's got no height, so therefore can cancel out the gravitational potential energy, leaving us with just the final kinetic energy. So that's going to go ahead and be 1/2 mass times velocity squared, and the velocity final. Okay, so we have then 1/2, the mass we don't have, we're going to multiply times the velocity, which they mentioned was 40 meters per second squared. So that's going to go ahead and give us the following. The final mechanical energy is going to be, let's see, 1,600 times 1/2, so that's going to go ahead and be 800. And times m, I'm going to leave out the units, so that way, just to declutter the problem a little bit, let me double check my math. 40 times 0.5, 800, so that's correct. Alright, so this is what we started with, that's what we finished with. So how much went away? Well, first of all, let's go ahead and figure out what fraction of this is that. Okay, alright, or we can figure out what's missing here. Alright, so what's missing will be 5,000 minus 800. Alright, so how much mechanical energy is the change in mechanical energy? That's going to go ahead and be final minus initial, 800 minus 5,000. So that's going to go ahead and give us 4,200 m. Alright, so that's how much was dissipated, that's how much is missing from here to there. Next, what percentage is that of the original amount? So it's going to be 4,200 m divided by 5,000 m of the original amount times 100, because they want a percent. So the m's will cancel out. So like I said, we didn't really need the m, so we don't have the mass of the apple, but that's irrelevant. So that is 4,200 divided by 5,000 times 100, that gives us 84%. 84% of the energy was dissipated by friction with the air. Alright, that goes ahead and takes care of problem 20. The answer is letter D, 84%. Our next problem is number 21. It says object X and Y are connected as seen on figure 1. So here we have it. There's X, there's Y, there's a pulley right there and a string. The mass of object Y is greater than that of object X. So this is heavier. Then they ask you, as the object Y falls, how does the gravitational potential energy of the whole system change? All the frictional forces are considered to be negligible, so you can ignore them. Alright, and in this one we're giving all these options, so A, B, C, D. And let's go ahead and talk a little bit about it. Alright, so where is the center of mass right here in this diagram? So this is our before. So let's say the center of mass, I would draw a line from the center of this one to the center of that one. Is the center of mass smack in the middle? Not quite, because object Y's got more mass. So if this is the middle, I would say that the center of mass will likely be there. Now, the after, object Y is heavier, so it falls to the ground. Where's the center of mass now? Well, again, I would draw a line from the center of this one to that one. Here, if this is the middle, would it be again in the middle? It's like, no, again, Y is heavier, so it would be slightly closer to the Y. Now, if you go ahead and you compare what happened to the height of the center of mass, and you see that there is a change in center of mass after it is lower, so therefore, if the center of mass is lower, it has lost some potential energy. So the answer for this one will be D. The gravitational potential energy decreases because the center of mass of object X and object Y moves down, as you see in this picture. And that's the answer for problem number 21. Up next for us is problem number 22. In this problem, they ask you the following question. It says a block of mass M is sliding on with an initial speed of VI along a horizontal surface of negligible friction. A constant force of FA is applied at a 60-degree angle upwards from the horizontal, causing the object to speed up. if the block remains in contact with the floor, so it doesn't come up or down, it remains in contact with the floor, what is the change in the block's kinetic energy as it moves along the horizontal distance of delta x? So you got 4 formulas right here, and they want you guys to go ahead and figure out what's going to be the change in kinetic energy or for this. Alright, so we're going to go ahead and here's our diagram. So we have force going at 60 degrees above the horizontal, mass is m, distance is delta x. We're going to use these two formulas to go ahead and solve this problem. First of all, work is equal to change in kinetic energy plus change in potential energy. Alright, now since the block's staying on the ground, initial and final height are 0, so therefore we can go ahead and cross this one out. There's no change in height. Alright, so, and work is equal to force times distance. So now we're going to go ahead and say, well then change in kinetic energy, since they both equal work, is equal to force times distance. Alright, so the distance we have it is delta x, so we know we're going to substitute that here. But what do we put for the force? Well, we want the force to be parallel to the displacement. So we are going to want this formula right here. This component of that vector, that's what we're looking for. So since it is adjacent to the hypotenuse, to the angle, that's going to go ahead and there be cosine. So cosine of 60 degrees is equal to this, let's just call it x, times over the force that's pulling on it. Alright, so that distance right there, that's going to be our force that we're interested in, is really this. If you move it around a little bit, Fa times cosine of 60, that's going to be our force for this part. Let's just label it as F for this part, F. Alright, so now we got that, we can go ahead and plug that in here. You have the distance, plug it in right there, and that's going to give us our change in kinetic energy. So change in kinetic energy is going to go ahead and be Fa times cosine of 60 multiplied times d, which they said use delta x. So there's our formula for change of kinetic energy. So now you look over here and you start to find it and you don't find it. Alright, this problem's a little bit on the tricky side because it's there, it's just hidden. It's actually letter A, that is your answer. 1/2 force A times the distance. And you're like, alright. So how does that formula? It's exactly that one. This right here. The cosine of 60. Put in your calculator. What is cosine of 60? The answer for that is 1/2. Alright, so that is really Fa times 1/2 times the distance. And they got it with the half in the front, so there you go. That is your formula for the change in kinetic energy. So the answer for problem number 22 is letter A. Alright, this brings us to the end of this week, and thank you so much for watching.